Hey everybody, and welcome to the second video on PDEs. You are watching this video because I am on pseudo paternity leave for 2 days and we can't afford to miss material for 2 days. So in this video we will just continue the trajectory we began last time in studying PDEs. So last time I defined what a PDE was for you and we looked at some basic examples. In this video, we will now look at a real class of PDEs and talk about how to solve them. So the PDEs we will be interested in this video are these. So PDEs of this form. You can have any function of x and y times ux plus any function of xy times uy equals 0. So the technical term for what we are studying today are first order linear homogeneous PDEs. Okay, so that's sort of a mouthful. The homogeneous means you got a 0 over here. First order means that you don't have uxx, uxy, uxxxxx, whatever, right? So you only have first order partials. First order partial with respect to x, first order partial with respect to y. Linear basically just means that you're not squaring them or cubing them or taking sine of them or something. Okay, they are just as they are. No powers, no whatever. So we will study equations that look like this. So by the end of this video, you will know how to solve any equation that looks like this, in principle at least. Okay, so if this f and g are complicated, you won't actually be able to solve the PDEs. But I'm going to give you a solution method that works in principle for anything that looks like this. And it's a pretty nice little argument, or a pretty nice little method. It's very geometric in flavor. So let's start by just looking at constant coefficient functions. So that's sort of the most natural starting place. So if f and y are f and g are super complicated, we might not be able to get any traction. So let's start in the simplest possible case when f is a constant and g is a constant. And let's think about how to solve this equation. We're going to use some geometry here. It's Calc 3 geometry that will in principle work when you replace a and b with non-constant functions. So here's the Calc 3 geometry we'll need. It's an observation that just runs on the definition of directional derivative. So I do not want to take the time here to review what they are. They're in section 14.6 of Stewart. Okay, sorry for the typo there. Stewart, rest in peace. I did not mean to misspell his name. So you can look back in your textbook, section 14.6, or just Google directional derivative and read the very nice Paul's online notes. But basically, the directional derivative of u at a particular spot measures how u changes in the direction of that vector. So this is a concept you would have been drilled on in Calc 3, and we need it now. This here is the directional derivative in the direction of this vector. So if you look back in section 14.6 of Stewart, you will see this formula here written, that the directional derivative of a function in the direction of this vector is this. Take the first component of the vector times ux plus the second component of the vector times uy. So again, it's trying to measure how the function changes if you move in the direction this vector is pointing. So if the function falls, so you have some sort of downward slope, as you move in this direction here, as you move in the direction of 1, 2 or something, whatever, this directional derivative will be negative. It will tell you you are falling in that direction. Okay, anyway, so I want to focus on the PDEs. If you have trouble with this concept or you don't understand what Paul's online notes are saying, whatever, just send me an email or we can talk about it when I get back. I'm still checking my email fairly frequently, so I should be able to respond to you within 24 hours. But anyway, when I get back from my pseudo fake short paternity leave, I'll just open it up to questions and you can ask me whatever you want. Okay, so the PDE itself, this thing up here that we're solving, and by the way, those of you who are in the math seminar, don't judge my slides. I know that your slides look way better than mine. Okay, I'm a simple man with simple slides. Okay, so I don't know all of your slide trickery, so don't judge me anyway. Okay, so this PDE here, well, it says that the directional derivative in the direction of AB is 0. Okay, that's what it's saying. So uxy must have no rate of change in the direction of that vector. Well, no rate of change simply means that you are constant in that direction. Right? So uxy is constant on any curve whose tangents are given by this vector. Okay, so the question is, how could we describe the curves in the plane whose tangents are given by that vector? Okay, so before we do this, let me just restate what's saying, what this PDE is saying. The PDE says the directional derivative in the direction of AB is 0. All right, so that means that uxy must be constant on anything that's moving in that direction. The things that are moving in that direction are curves whose tangents are given by this vector. So all we need to do is figure out what curves in the xy plane have tangents that look like this vector, and we will then know that u must be constant on those curves. Because u, again, is not allowed to have any change in the direction of this vector. The change is 0. The directional derivative is 0. Okay, so we want to know the curves in the plane whose tangents are given by this vector. That will tell us where u is constant. Okay, well, if you want to know tangents are AB, well, this is going to look kind of silly here, but I want to use this technique later, so I'm going to do it in full generality here. So if you want to know where the derivative, where its slopes, right, have this particular form, like this is the y component, this is the x component, right, the derivative of any of those curves is y over x, right, b over a. So what you get here is an ODE. This is saying the rate of change of y with respect to x, where we're just in the normal xy plane. So y depends on x only. This is saying that in the xy plane, dy dx is just b over a, which is just a number. But at the very least, this is an ODE. There are no partials here. So again, not all of you have had an ODE course, so let me just show you how to solve something like this. It's pretty straightforward, and we're going to use this technique later. You use something called separation of variables, where you just treat this dy dx as a fraction, and it's not totally clear that you're allowed to do that. It's not clear that you're allowed to treat this as a fraction, but I, as your PhD professor, whatever, right? I'm telling you it's fine. You just have to trust me, right? Like, just take my hand and follow me here, everything will be fine. So you treat it like a fraction, which means you can shift that dx over here, and then you can integrate both sides. So you're integrating a 1 over here, and integrating the number b over a here, and the integration itself gives you this, that y is b over ax plus c. Okay, so these are the curves in the xy plane that go in the direction of v, this vector v here, AB. So these are the curves in the xy plane where u must be constant. Right? U is constant on anything that's moving in the direction of AB. So any solution u of the original PDE is constant on lines of this form. And it cut off, all I did was solve for c here. So let me see if I have written, yeah, so if you solve for c, let's go through that. You multiply both sides of this equation by a, you get an ay, a bx, and a little ac, but c is any constant, so c just absorbs that a, and then you can shuttle the x over to the other side, or the y over to the other side, doesn't matter. Okay, so the solution u of the original PDE is constant on any line of this form. These lines are called the characteristic lines. So anything on which you are constant is called a characteristic curve. And so in this particular case, your curves are lines. Therefore, the function u, the solution you are interested in, at a particular point, depends only on the line on which that point happens to live. Okay, u is constant on any of these lines. So if I want to know what u of xy is, all I have to do is tell you what line it lives on. So as you move along a line like this, the values of u don't change, because again, u is constant on these lines. What does that mean? That means that u of xy only depends on what line it's on. So u of xy is a function of the line that the point lives on, where f here is just any function of one variable. So this looks kind of strange, but let's unpack what's happening here. So on the line bx minus ay equals c, the solution u has a constant value because, again, u, sort of by definition, right? U is constant on those lines. So let's call this value f of c, right? Just depends on the constant value. The constant determines which line you're on. Then u of xy equals f of c. Oh, but c is bx minus ay. So since c itself is arbitrary, you can put it wherever you want in the plane, which just corresponds to shifting this line up or down. We have this formula. U of xy depends only on the line that you are on for all values of x and y. Okay, to make this concrete, let's think about a function of a single variable f. So let's say f of t is t squared. Then u of xy is f of bx minus ay, like we have here, right? So u only depends on which line you're on. It's a function of the line you're on. But if f of t is this particular single variable function, right? So if f is just the function that squares things, then f of bx minus ay equals that function. Okay, so let's just take this guy and substitute it back into the original equation and see what we get. So aux plus buy by the chain rule equals, so aux, there's your a, right? And then ux, you got to bring the 2 down, right? And then scale by the partial with respect to x in here, which is that b. And of course, once the 2's down, you leave the inside alone, right? So this is just the chain rule. So you get a 2ab minus, 2ab times the quantity bx minus ay. Then you got to add buy. So there's your b. And then the chain rule here, now you got to do it with respect to y. You bring the 2 down, multiply by a negative a, which is why you got a negative a. But notice that equals 0, right? So it turns out that if you take bx minus ay and square it, you get a solution of this original equation. But the squaring is irrelevant. I could have cubed it. I could have signed stuff, you know, like I could have done not t squared but sine of t, and then right here I would have had sine of bx minus ay. It doesn't matter what this function f is. As long as you're plugging bx minus ay into it, you'll get a solution of this equation up here. So if you change f to any other function, you yourself might want to verify that for sine t, e to the t, whatever. You will still get a solution of this PDE. Because again, all that matters is the line you are on. That's all that matters. As soon as you know the line you're on, then everything else is determined. So you can take that line and do whatever you want to it, but the lines itself determine the solution. So to show that this guy is a solution for any f, so not just t squared or something, note that by the chain rule, aux plus buy equals, you got your a here, and then again, if u is this, right, the chain rule says prime the f, leave the inside alone, multiply by the derivative of the inside with respect to x, which is b. Then we got to add buy, and the chain rule says, well, to deal with uy, you again, f prime, so prime the outside, leave the inside alone, and now multiply by the derivative of the inside with respect to y this time, right, uy, which is a negative a. And so notice, you got an ab f prime, negative ab f prime. So those guys go away, and you get 0. So anything that looks like this is a solution of the original PDE by the chain rule. So this sort of thing takes getting used to, and it's sort of weird to write, but this is all that you write. This is your solution set, right? So f of these lines, where f is any function of a single variable. That's your solution set. So this process we did here will extend quite naturally to any other function. So if a and b aren't constant, you can still write down this ODE, and you can solve it by separation of variables sometimes, at least for the ones we will do, and then you get the curves on which the function is constant, and once you know those curves are all that matter. U will be a function of those curves. So let's do this for a couple more examples. Oh yeah, first, you think about this one. So this one is still constant coefficients. In the interest of time, I'm not going to go through everything myself, but go ahead and pause the video and see if you can solve this equation. Okay, so assuming now you have unpaused the video, I will throw the solution up here. The analysis goes exactly like we did before. You just actually fill in what 3 is a and b is -2, and you will get that u of xy equals f of -2x minus 3y. So -2x minus 3y equals c. Those curves are where the function u is constant. So the value of u only depends on the curve that the point is on. So the value of u is a function of the curve you're on. That's what it's saying. And in this case, these lines. So I put another concrete example in here. Suppose f were e to the t this time. I don't know. So that uxy equals f of this stuff, this line, which now equals e to the -2x minus 3y, if f is this. So you can check that 3ux minus 2uy equals, you got to do the chain rule here, right? So the derivative of e to the x is basically itself, but then you got to put the derivative of so the 3 comes along, right? Here's the derivative of x right there, and then minus 2uy, so the 2 is right there, and you got e to the stuff again, times the derivative of the y part this time, right? So notice you got a -6 here, and a +6 here, and you get 0. So it doesn't matter what f is. F could be sine t, cos t, tan t, whatever, you know. As long as you're plugging -2x minus 3y into that f, you will get a solution of this PDE. Okay, but anyway, here's the solution set. And it goes just like we did in that example. Okay, now let's try an equation with non-constant coefficient functions. In this case, the function of, or the coefficient of ux is still constant. But now we have a non-constant function attached to the uy. So let's see how this goes. Well, it will go the same way, actually. Okay, so this PDE is saying that the directional derivative in the direction of 1y is 0 this time. So same thing as before, it's just if these coefficient functions aren't constant, you're still making a statement about a directional derivative. Because again, the directional derivative is just something times ux plus something times uy. So now we need to think about the curves in the xy plane with 1y as tangent vectors. And those guys, when you say 1y, you're just talking about change in y over change in x, right? So y over x. The slopes have this formula. So the rate of change is just y now, just y over 1. Just like before, where were we? Yeah, so y component over x component. The slopes are y component over x component of that vector. So it's the same thing here. We just now have that the slopes are y component over x component. Since the y component is not constant, we have a real live ODE here that's more interesting. Okay, so we now have dy dx isn't a constant, but it equals something that changes based on your y value. You know, so as you move up or down in the xy plane, you'll change the slopes. Okay, so this again, this is an ODE that if you took my course, this is the first ODE we solved in the course. So what is this saying? It's just saying find me a function whose derivative is itself, right? Find me a function so that y prime is y. If you think about it, this is something a Calc 1 student could probably tell you if they thought about it long enough. The functions whose derivatives are themselves are e to the x, but you can scale that e to the x by anything you want. So certainly the derivative of e to the x is e to the x, but the derivative of like 2e to the x is also 2e to the x, you know, etc. So you can take the e to the x and scale it by whatever you want. So on any curve of that form, a solution u, x, y of the PDE is constant, just like in the previous example. So again, the directional derivative in these directions is 0. But having a directional derivative of 0 means there's no change in that direction, which means you are constant in that direction. So you are constant on these curves. In this case, you have exponential curves, right? In the previous example, we had lines where we were constant. But in this case, we have exponential curves on which we are constant. Okay, so on any curve of that form, a solution of the PDE is constant. So by the same logic as before, I just solve for this constant, and I get y e to the negative x. So just like back here, where was it? Yeah, okay, here. So I solve for this variable, or this constant c there, to get this equation of my lines. So all that matters is the constant, because the constant tells you which of these exponential curves you're on. So as soon as you know the constant value c, you know which exponential curve I'm on. I'm on that one, you know. So u only depends on that c value. It only depends on which of these curves you are on. So u is a function of the exponential curve you are on. That's what this is saying in English. U is a function of this curve. U only depends on the curve, this exponential curve, where again, f is a single variable function. So just again, to make this more concrete, let's pick a single variable function. So let's pick like sine t. That would mean that u of xy equals f of e negative xy by definition. That's just from the last slide, right? Just copied that. But since f is a sine, that just means you're taking this stuff and plugging it into sine. So let's just check that u is a solution. ux plus yuy equals, now we got to do the chain rule, right? So we got to coast this guy. And then ux. Yeah, so ux is, you got to bring the negative down, and the y is acting like a coefficient. So this is what you get for ux. Plus yuy. So again, to do uy, we got to prime the outside guy, leave the inside alone, and then multiply by the partial with respect to y, which in this case is e to the negative x. And notice these two guys are negatives of each other, right? So they add to 0. So here's a concrete solution. Sine of e to the negative xy is a concrete solution. It looks like those those curves on which we are constant, just some function of them. So to check that anything of this form works, we can just use the chain rule. So here's that computation here. Ux plus yuy equals, you prime the outside guy, right? Leave the inside alone. You got your partial with respect to x of the inside sitting here, plus a y. Prime the outside, leave the inside alone, partial with respect to y is here, and notice no matter what that f is, right, you have a negative guy here, positive of the same thing, so they add to 0. So all those guys are solutions. F could be sine, cosine, t squared, t cubed, root t, whatever, right? All these guys work. So you try this one. See if you can handle this. So again, I will pause the video, or sorry, you should pause the video and then see what you get, and then we'll walk through the solution. Okay, so here's the solution. It's the same logic as before. Now the directional derivative in the direction of this vector, x1, is 0. So the curves in the xy plane with these as vectors have slopes 1 over x. And how do you describe those guys? Just like the previous example, here's an ODE describing those curves. So if you want the curves themselves, you can separate variables as we've done before. And so you get dy equals 1 over x dx. You integrate both sides. The left-hand side becomes a y. The right-hand side becomes log of absolute value plus some constant. Therefore, a solution u is constant on any curve of the form y equals log absolute value of x equals c. So your solution values only depend on this capital C value. Only depends on which of these curves you're on. So a solution of the PDE is anything of this form. F of that curve, where f is a single variable function. Okay, so there you go. So I just wanted to do one quick last example just to make one of the guys more complicated. So before we had just the x stuff or just y stuff. Here's a mixture of the two. So now we have a coefficient function that's a mixture of x's and y's. So just to go through this real quickly, the logic is exactly the same. Okay, so the characteristic curves satisfy this, just y over x. Those are the curves on which you are constant, just like in the previous examples. So to solve this ODE, you again just separate variables. So you shift that dx over here. You got to shift the y squared over here. You have to group x and y stuff, so that when you integrate, you're integrating just a dy guy, just a dx guy here. Integrating both sides yields this equation. So if we just isolate that c and we get our -1 over y minus x squared guy, these are the curves on which a solution is constant. Therefore, the solution only depends on which of these curves you're on. So the solution is a function of the particular curve you're on. And the general solution is this. U is a function of whichever of these curves you are on, where again, f can be any single variable function. Okay, so, it's kind of awkward making videos because I can't watch your little faces as I say this to you. So I have no idea if, where's the very first one we did? I have no idea if this statement here, where is it? This statement here makes any sense to you at all. It takes kind of some getting used to, saying that the value of your u function, which depends on x and y, only depends on a particular line through 2 space. Okay, so that takes some getting used to. So I'm hoping that if you're confused by this, the first thing you will do when I get back on Friday or whenever, I'm hoping the first thing you will do is ask about this so we can talk about it in person. Okay, so we are now done with our videos, and I'll see you back in class.